是沉默，分开了就痛，是不是说没有做完的梦？
Hello, we are Group 13, and the topic we chose is metronome synchronization. First, let me introduce our group member. We have Danny Fan, and me, and Alex Wang, and Albert Wu,
Hello.
and Justin Su.
Hi.
Okay, now let's talk about our motivation, namely why we choose this topic. At first, our original topic is star observation. However, the weather in Hsinchu sucks. The flowing clouds ruin our shot every 15 minutes, and the light pollution was very severe. As we can see here, our goal was this, and what we actually got was this. Yeah. So we abandoned this idea and sought out for a more steady and measurable topic. And by the second law of the thermodynamics, everything in the universe seems to be disorder, such as my room. Chaos is the norm in the complex system, and we will naturally expect the universe to be messy. However, we can still observe some spontaneous orders around us, such as the star's periodic orbits, the synchronization of the bridge, the sync of the fireflies, the sync of the cats, and the synchronization of the metronomes. We thought that the metronome synchronization is interesting and practical topic, so we decided to use this as our topic. And these are our goals. First, to analyze the time for the metronomes to be synchronized for different starting phases or different starting frequencies. And second, try to create time measuring devices using the synchronizing mechanisms of the metronomes.
Okay, I'm Danny Fan. Let me explain the physics behind the metronome resonance. First, we want to talk about the key theorem for the synchronization. We find a model called Kuromato model, and the model is shown here. Which in this equation, the omega is the natural frequency or eigenfrequency, which is the original frequency of the object, and this K is Kuromato constant. When K increases, the system needs more time to synchronize. On the other hand, when K decreases, the system needs less time to synchronize. And so let's explain more about the motion of a single metronome. We after some computation by analysis toward kinetic energy and potential energy, we can get this equation, and note that we have take the driving force with van der Pol turns into concern, and the theta is the angle of the pendulum makes with the vertical. The RCN is the distance of the pendulum center of mass from the pivot position, and I is the moment of inertia of the pendulum, and this epsilon ideals equals to 0. And let's move to two metronomes on a moving base. we use Euler-Lagrange function, we can get the following result. And this theta 1 and theta 2 is the angle of the first or second pendulum mixed with the vertical. And this big capital M is the mass of metronome without pendulum. And this small n is the mass of pendulum. And this mu is the epsilon. And beta and delta and omega is shown here. And let's see our simulation result from the previous equation. We can see that the system of two metronomes is similar with the coupled oscillator. Two objects in the system will influence the energy of the others. It can be seen that the angle will vary with time, but actually, the metronome we bought have torsion spring. The energy will continue to enter the system, so the angle actually will not decrease that much. And this is omega 1 and omega 2, and this is this omega 1 dt d omega 2 dt. Okay, let's take a short look of my Python code, how to realize that equation. And this part is our parameters, and yeah, it's typical value. And we use iteration, yes, here, to calculate our theta 1, theta 2, and d theta 1 dt, and d theta 2 dt, and yeah, and so on. And finally, we plot our result. Let's review some simulation result which we have already shown in the mid-report. First, we look at the left-hand side. We can see that there are 3 metronomes starting from 3 different phases, and it will eventually become in the same phase as time passes by. And the right-hand side is the x-axis is cosine theta and the y-axis is sine theta. And the black dot here is the average theta of these 3, and it will finally become a dot 2 as time passes by.
Next is our practical implementation. We first do experiment on 2 metronomes with the same frequency, and as expected, the result is quite similar to what we have done on Python. So it will start at different phases and then eventually resonance at the end. And with the success in 1 dimension, we soon move on to 2 dimensions. With 2 different experiment approach. The first one is like this. We cascade the board and put the metronomes in a cross at both x-axis and y-axis. But after analyzing in tracker, we found out that they will not reach synchronization. So we did the same thing again, but in a different way. We changed the bottom of the board to 4 bolts, but the result is quite the same. And then we make up a circle with 6 metronomes. But the result is still not as expected. And you can see it, we put the video in tracker.
and the data is on the right hand side. We at first expect the result would be a circle, or at least a cyclic motion, but you can see in the right hand figure, the result is quite a mess.
Okay, let's look at the problem we faced and what reasons make us fail many times. First, because the measurements are made in China, the measurement didn't work as well as we thought. One of them cost us 380 NT dollars, and we buy 6, but only 2 of them can use in this project. Actually, all the measurements are inaccurate. For example, we set up the frequency of the measurement as 176 BPM, but when we use app to check the frequency, it showed that the measurement only 170 BPM. 2 of them can use only due to they have the same inaccurate frequency. Second, in 2D, the acceleration of the board underneath is too small to observe. Even if we use the tracker to check the path, see the path as the time goes on, we are still hard to analyze the regular data. In order to avoid we get failed in ODE class as the project failed, we find another way to continue our project. Those way measurements still can be used. We observe the 2 measurements with frequency difference have cyclic variation when they try to get synchronization. In theory, different frequency can make 2 measurements synchronize, but we found that the synchronization still happens when the difference of the frequency of 2 measurements is small. Next, we invite X1 to intro Python validation.
First, we use the Kuramoto model, and this is a Kuramoto constant. It's about how strong the metronomes are connected and affect other metronomes. And we measure the time how long 2 metronomes synchronize by experiment of our metronomes to decide this constant. N is the number of metronomes, and dt is the accuracy of the simulation. Time m is the simulation time. For instance, its simulation simulates from 0 seconds to 60 seconds. Then we'll set up the initial condition. Theta means its current phase, and omega is the frequency of the metronome. And here's our result. When the frequency of the metronomes are close, they'll synchronize forever. And observing this graph, we can see that the phase difference converges to 0. Then we use the above data to make some GIF.
By using the data, we can make our simulation of metronomes.
What if the difference of the starting frequency increases? We can find that 2 measurements are starting at the same phase. As time goes on, the difference of the phase increases to pi. And then decrease to same phase. What a perfect cyclic variation to measure time.
So we put this interesting phenomena into analysis, and you can see, just put it in tracker and it will automatically track the motion for you. And you can see the result actually acts like a clock. They first start at the same frequency, at the same phase, and after about 30 seconds, their phase difference reach pi, and after another 30 seconds, they reach the same phase again. And then Wang Hongmin will introduce the Python realization.
And from Python simulation, we can see that when the difference of the frequency of the metronome becomes larger, we can observe that they will not synchronize forever. Instead, they will have periodic phase difference. For example, we choose metronome with frequency difference of 8 Hz. We can get a result of about 30 seconds a cycle, and 2 metronomes will reach phase alignment.
And this is our simulation of metronomes.
Finally, we take a quick look of our Python code. And first, we set our Kuramoto parameters. Then we use Kuramoto models, formula, and iterations to calculate zetas. And we can get our result. And we made 3 different animations. And first one is cosine theta of t, and some magnificent dot. And finally, we draw 2 metronomes.
Finally, the conclusion. First, we know that synchronization only happens when the frequency difference of the metronomes is very small. And secondly, as the frequency difference of the metronomes increases, their phase relation acts like a cyclic motion and can be implemented as a clock. And to take it up to the next level, we want to find out the relationship between the frequencies of the 2 metronomes and the phase alignment period, creating a clock with the arbitrary period. And that is our presentation. Thanks.
钱乱玩啦。